Hi everyone. Today we're going to be talking about stoichiometry and specifically how we can use stoichiometry to calculate what is called molar volume. So before we get too invested in this, let's take a step back to what we had been doing previously with our stoichiometric process. So if we look at this sample problem, this should be an arrow right here. First thing we're going to do is balance it. So if I look at this equation, my aluminum oxide over on the right, the oxygens come in threes. So what that means is I'm going to have a common denominator, or a common multiple between 3 and 2. Because if I double this, right, so if I put 2 out in front of the aluminum oxide, that's going to allow me to have 6 oxygens on the right. In order for me to get 6 oxygens on the left, I want to put a 3 there. And then I also want to make sure my aluminums are balanced, and that's going to be a 4. So I'm just going to go through and highlight those numbers because that's what we are going to use to find our mole ratio. The type of reaction this is, 2 different elements are coming together to become one product. So this is a synthesis reaction, okay? So how we would then calculate and use it is by looking at what we're provided with. So it's telling us that we want to calculate the mass of aluminum needed. So that's going to be my unknown mass of aluminum. And I know that I'm starting with 25 grams. So if I want to produce 25 grams of aluminum oxide, how much aluminum would I need to make that much? So the way that you set that up, start with what you're given. So the 25 grams of aluminum oxide, that's how much I need to make. I'm going to convert that from grams to moles. Okay, so I'm going to add up the 2 aluminums and the 3 oxygens. What we find, that is 102 grams in 1 mole. We're then going to use the mole ratio to go from moles of Al2O3 into moles of aluminum. Based on my balanced chemical equation, again, I'm just pulling those numbers that I used for balancing. I'm just going to pull those and put those in the mole ratio. And just to keep tabs and make sure we're crossing out our units, the units we should have left are moles of aluminum. So now I want to convert moles of aluminum into grams of aluminum. So I look on the periodic table, I find aluminum, and it has a mass of 27 grams. This then is equal to 13.23 grams of aluminum, okay? So just another quick practice. Last time we were starting with grams. This time we're starting with moles. And ending with grams, you always have 1, 2, 3 steps. Looking at this next one, so here, same exact chemical reaction. We're going to be doing the same process. So now we have mass of oxygen. That's what we want to find, so that's where we're going to end at. But we're starting with moles of aluminum. So when you're starting with grams, when you are starting with moles and ending in grams, you're only going to have 2 steps. So it's only going to require 2 steps here because we're already starting in moles. So I don't need to take the time and the step to convert grams of aluminum to moles of aluminum. It's already in moles of aluminum. So I'm just going to put 4 moles of aluminum on the bottom. I'm converting it into moles of oxygen. Moles of aluminum crosses out. And then I need to convert that to grams of oxygen because I'm being asked for mass. So 1 mole of O2 has a mass of 32 grams. This is equivalent to 17.4 grams of O2. So this is great, like a review of just what we've done before, but what happens if I was asked to find the volume of oxygen? So volume is, I'm just going to put this off to the side, how much space something takes up. So if we think about a gas, I can't put a gas on a scale and measure it. That's not really possible because gases float away. So instead, we measure gases by volume, how much space they're taking up. So think like a balloon. If a balloon is really heavily inflated, it has a bigger volume than something that's not very inflated. So if we wanted to try to figure out the volume of oxygen needed, we're going to need to do things slightly differently. So as a result of this lesson, you're going to learn how to calculate the volume of a gas as opposed to the mass of the gas, okay? So The thing you need to remember, this right here that I'm circling like 20 times, 1 mole of any gas at standard temperature and pressure is going to take up 22.4 liters of space. So I'm going to, well, I really wanted that to erase the whole thing. Okay. But nope. Okay. Well, I guess this is the best I got. So I want to write this down as a conversion factor because it's nice writing it down like this. But we're going to be using this as a conversion factor. So the other way I can write this is 1 mole, 22.4 liters. And liters is how we measure volume. Okay, so if I think about like a liter of gas, it's just how much space it takes up. And for any gas at standard temperature and pressure, so that's standard temp and pressure, it's going to take up 22.4 liters of space. Doesn't matter what the gas is, doesn't matter anything else, as long as it is at standard temperature and standard pressure, it's going to take up 22.4 liters of space. So this is the new conversion factor we will now use. Wrote here can be subbed in. So this conversion for steps 1 or 3. Remember, step 2 is going to be the mole ratio. This never changes, okay? So step 2 is always a mole ratio. But if I'm starting with liters of a gas, I can convert liters to moles, moles to moles, and moles to grams or liters. So I'm basically, this is now being sub for molar mass. So if I'm being asked or working with volume or liters, instead of using the molar mass step, I'm now going to use this new conversion factor here. So let's take a look at what this looks like. So we're still working with the same equation we were looking at before with the aluminum, the oxygen, and the aluminum oxide. But now we are going to find the volume of oxygen, that's our unknown, if we're starting with 0.725 moles of aluminum, okay? So before, when I did this, I just set up a mole ratio because I'm in moles of aluminum, so I don't have to do a molar mass step. It's already done for me. So moles of aluminum is going to be converted to moles of oxygen because we're trying to get to oxygen. So it's 3 and 4 respectively. Moles of aluminum crosses out. And now, because I'm finding volume, I know, this is my new conversion factor, there's 22.4 liters in 1 mole of any gas, okay? So 1 mole of oxygen is going to take up 22.4 liters of space. That's the volume. So instead of me finding molar mass, like I've done up until now, now I'm just using our new conversion factor. This then tells us that it would be 12.2 liters of oxygen. So let's try another one. So now we want to figure out the volume of oxygen needed, so that's our unknown, if we want to react 10 grams of aluminum in STP. So if we think about how many steps, we're first going to go grams to moles. That's one step, okay? That's our first step. Then we're going to convert that to moles of our unknown. That's our mole ratio step. And then we're going to convert it to volume, which is in liters. So this is 1, 2, 3 steps, okay? Just like we saw grams to grams. So we're going to start with 10.0 grams of aluminum. My first step is converting grams to moles. So grams and moles. If I look on the periodic table, 1 mole of aluminum, 27 grams. Grams crosses out. My next step is to convert it from moles to moles of our unknown. So I know I'm starting with aluminum. I'm trying to find oxygen. So now I look at my balanced equation, 3 moles of O2, 4 moles of aluminum. Moles of aluminum crosses out. Now I need to do this third step, converting moles of my unknown into liters of my unknown. And I remember there are 22.4 liters in 1 mole of any gas at STP, or standard temperature and pressure. So I'm going to want to put moles of oxygen on the bottom, liters on top. 22.4 liters in 1 mole. This is then equivalent to 6.22 liters of oxygen. So let's try one more problem together. This time we're going to be starting a little bit differently. Here we started with our first step being molar mass. Okay. Notice our next step, the thing that we always have, is the mole ratio. And then here we have our new conversion factor, molar volume. Okay. Molar volume is always going to be this conversion factor. So now let's look at this same equation, but now we're going to be trying to find the mass of aluminum oxide, Al2O3, if we have 4 liters of oxygen gas. So we're just working backwards. We're starting with liters of oxygen gas. So I'm going to go from liters to moles, then convert that to moles of Al2O3, then convert that to grams. So I'm still going to have 1, 2, 3 steps, just like before, except I'm working in a different direction. So I know for any gas at standard temperature and pressure, there are 22.4 liters in 1 mole. That doesn't change. So liters will cross out. Then we're going into our mole ratio. Moles of oxygen. I'm trying to find aluminum oxide. 2 to 3. So again, just coming right from my balanced chemical equation. And then finally, I'm trying to end in grams of aluminum oxide, so I'm going to need to convert moles to grams here for Al2O3. 1 mole of aluminum oxide is 102 grams if I add up the 2 aluminums and the 3 oxygens. Altogether, 12.1 grams of aluminum oxide. So hopefully at this point you're recognizing that volume of the gas is just a new conversion, which is 22.4 liters in 1 mole of gas. And this is being subbed for step 1 or 3, okay? So if I don't want to find grams, I can sub in liters and solve for that instead using this new conversion factor. So if you have any questions, let me know, but hopefully this isn't too tricky.